What if I told you that everything you think is solid, real, and certain is actually a phantom, a ghost made of possibilities? What if the chair you're sitting on isn't just here, but also a little bit everywhere else? This isn't a riddle from a fantasy story. This is the bedrock of our reality. We live our lives on the surface of a deep, mysterious ocean, and we've mistaken the surface for the entire body of water. We see the waves, feel the spray, but we have no idea about the strange, beautiful, and impossible creatures that swim in the darkness below. For centuries, we were content with this surface-level understanding. We built laws of physics that described the world we could see and touch with remarkable precision. We could predict the path of a planet, the trajectory of a ball, the mechanics of a clock. We thought we had it all figured out. But then, about a century ago, we dared to look deeper. We built tools that allowed us to peer beneath the surface, into the realm of the incredibly small, and what we found there shattered everything we thought we knew. We found a world that doesn't play by our rules, a world of pure potential, of spooky connections, of things being in many places at once. This is the quantum realm, and it's not some far-off, abstract dimension. It is the very fabric of you, of me, of the stars in the sky, and the ground beneath our feet. The journey we're about to take is a journey into that invisible ocean. It's a journey to understand the fundamental nature of reality itself. And it will change not just how you see the world, but how you see yourself within it. Because you are not just a passive observer of this strange universe. You are an active participant in its creation. Chapter 1. The World in a Grain of Sand. Imagine you're holding a single grain of sand on your fingertip. To you, it's a tiny, solid speck. Unremarkable. You can feel its weight, its texture. It is definitively there for most of human history. That was the end of the story. We believed that if you just kept cutting things in half, you'd eventually reach a final, indivisible little ball of stuff, an atom. A word that literally means uncuttable. This was a comforting idea. It meant the world, at its core, was solid and predictable, just like that grain of sand. But what if we could keep going? What if we had a knife sharp enough to cut that atom? For a long time, we couldn't. But then, pioneers of physics like J. Thomson, and Ernest Rutherford began to chip away at this idea. They discovered that the atom wasn't a solid ball at all. It was mostly empty space. At its center was a tiny, dense nucleus, and orbiting it, like planets around a sun, were even tinier things called electrons. Suddenly, that solid grain of sand wasn't so solid anymore. It was a miniature solar system, a whirring dance of particles in a vast void. But the real revolution came when we tried to understand the rules of that dance. The old rules, the ones that worked for planets and baseballs, completely broke down. It was like taking the rulebook for chess and trying to use it to play a game of poker. It just didn't work. The particles inside the atom behaved like nothing anyone had ever seen. They didn't have a definite location. They didn't follow a neat, predictable path. They existed in a haze of probability, a cloud of maybes. This new set of rules, this new language to describe the subatomic world, became known as quantum mechanics. The word quantum comes from the Latin for how much, and it points to one of the first and most shocking discoveries of this new science, that energy in this tiny realm isn't smooth and continuous. It comes in discrete little packets, or quanta. Think of it like a ramp versus a staircase. Our old physics saw energy as a smooth ramp you could be at any height. Quantum physics revealed it was a staircase you can be on step 1 or step 2, but never in between. This might sound like a small detail, but it was the first clue that the fundamental nature of reality was pixelated. It wasn't a smooth, high-definition movie. It was made of tiny, indivisible frames. So, that grain of sand is no longer just a speck. It's a universe teeming with trillions of these little quantum dramas, each one playing out according to a set of rules that defy all common sense. This isn't a flaw in our understanding. It's the discovery of a deeper, more fundamental truth. The world we experience, the solid, stable world of our senses, is an illusion. It is an emergent property, a collective agreement reached by countless quantum particles, all following their strange, probabilistic dance. Understanding this is the first step on our journey. We must let go of our certainty, our belief in a solid, classical world, and be willing to embrace the weirdness. We have to be willing to see the entire universe, with all its mystery and wonder, in that single grain of sand. And as we venture deeper, we will find that this weirdness isn't just a curiosity of the subatomic world. It has profound implications for everything, from the way a star shines to the very nature of consciousness itself. The first and most mind-bending of these quantum rules is one that challenges the very idea of existence. It suggests that before you look at something, it doesn't really have a definite state. It's caught in a ghostly limbo, a world of pure potential. We're about to explore this ghostly state, a concept so strange it has its own famous and perhaps misunderstood cat. Chapter 2. The Ghost in the Machine. Have you ever felt caught between two choices? For a moment, you exist in a state of pure potential. You could turn left, or you could turn right. Both futures are equally real possibilities, hanging in the air until the moment you decide. In our everyday world, this is just a metaphor for indecision. But in the quantum realm, it is a literal truth. This is the principle of superposition, and it is perhaps the most fundamental and bizarre aspect of quantum mechanics. It states that a particle, like an electron, doesn't exist in one single state until it is measured. Instead, it exists in all of its possible states at once. It's not in one location, it's in a cloud of potential locations. It's not spinning up, it's not spinning down. It is in a ghostly combination of both up and down simultaneously. To help us grasp this, let's use an analogy. Imagine a coin, not sitting on a table as heads or tails, but spinning perfectly on its edge. While it's spinning, what is it? Is it heads? Is it tails? It is neither, and yet it is both. It is in a superposition of heads and tails. It holds the potential for both outcomes, but it hasn't committed to one. Only when you stop the coin, when you interact with it and force it to land, does it choose a state. It becomes either heads or tails. In the quantum world, observation is the act of stopping the spinning coin. Before an electron's position is measured, it behaves like a wave, spread out across space, embodying all possible positions. The moment you measure it, the moment you look at it with a detector, this wave of potential collapses into a single, definite point. The electron suddenly has a location. This is what the physicist Erwin Schrödinger was trying to illustrate with his famous thought experiment involving a cat in a box. It wasn't a real experiment, but a story designed to show how absurd the consequences of superposition would be if they were scaled up to our world. He imagined a cat in a sealed box with a vial of poison, a radioactive atom, and a Geiger counter. If the atom decays, a purely random quantum event, the Geiger counter will detect it and trigger a hammer that smashes the vial, and the cat dies. If the atom doesn't decay, the cat lives. According to superposition, until we open the box and look, the atom is in a combined state of both decayed and not decayed. Therefore, following the logic, the cat, whose fate is tied to the atom, must also be in a superposition. It is both alive and dead at the same time. This paradox highlights the jarring disconnect between the quantum world and our everyday experience. We never see a cat that is both alive and dead, but in the subatomic realm, this is business as usual. This idea of superposition isn't just a theoretical curiosity, it's the engine behind some of our most advanced future technologies. The dream of quantum computing rests entirely on this principle. A classical computer bit is like a light switch. It can be either on or off, a 1 or a 0. A quantum bit, or qubit, is like that spinning coin. It can be a 1, a 0, or both at the same time. By harnessing this ability to exist in multiple states at once, a quantum computer can perform a massive number of calculations simultaneously, promising to solve problems that are currently impossible for even the most powerful supercomputers. So, the next time you feel indecisive, remember the quantum particles that make you up. You are, for a moment, living in a state of superposition. You are a wave of potential, ready to collapse into a new reality. This principle forces us to accept that the world at its most basic level is not one of certainty, but of probability. Things are not as they are as they might be. But the quantum weirdness doesn't stop there. If superposition challenges our idea of what it means for something to be, the next concept we'll explore challenges our idea of what it means for things to be separate. It suggests a deep, mysterious connection that binds particles together, no matter how far apart they are, in a phenomenon Albert Einstein famously called spooky action at a distance. Chapter 3. The Invisible Thread. Imagine you have two magic coins. They are perfectly linked. You give one to a friend, who then travels to the other side of the world. You stay here. You both agree to flip your coins at the exact same moment and let them land. You look down at your coin, and it has landed on heads. Instantly, with absolute certainty, you know that your friend's coin, thousands of miles away, has landed on tails. You check with your friend, and you are right. You try it again. This time, yours is tails. You know, without a doubt, that theirs is heads. It happens every single time. It's as if the coins are communicating with each other faster than the speed of light, whispering their results across the globe. This is not magic. This is a real quantum phenomenon called entanglement. It's a special connection that can exist between two or more particles. When particles are entangled, they are no longer independent entities. They become part of a single, unified quantum system, even if they are separated by vast distances. Their fates are intertwined. Measuring a property of one particle, like its spin, instantly influences the corresponding property of the other. If one is measured to be spin up, its entangled partner will instantly be found to be spin down. This happens instantaneously, regardless of the distance separating them. This is what so deeply troubled Albert Einstein. His theory of relativity had established that nothing, not even information, could travel faster than the speed of light. Yet here was a phenomenon that seemed to do just that. It appeared as though the particles were sending signals to each other instantly. He dismissed it as spooky action at a distance, believing that quantum mechanics was incomplete. He argued that the particles must have some hidden instructions from the moment they were created, like two gloves separated into two boxes. If you open one box and find a left-handed glove, you instantly know the other is right-handed. There's no spooky communication, just pre-existing information. For decades, this debate raged. Was it spooky action or hidden variables? Then, in the 1960s, a physicist named John Bell devised a brilliant theoretical test. Bell's theorem, as it came to be known, provided a way to experimentally distinguish between Einstein's hidden variables and the predictions of quantum mechanics. The experiments were incredibly difficult to perform, but over the following years, physicists like Alain Aspect, John Clauser, and Anton Zeilinger conducted increasingly precise tests. The results were overwhelming and unambiguous. Einstein was wrong. There are no hidden instructions. The universe really is that spooky. The connection is real, and it is instantaneous. The implications are staggering. It means that on a fundamental level, the universe is not a collection of separate, isolated objects. It is a deeply interconnected whole. The two entangled particles are not two things. They are, in a profound sense, one thing, just existing in two different places. This invisible thread connecting them transcends our normal understanding of space and time. It suggests a layer of reality where distance is meaningless. This principle is not just a philosophical puzzle. It's being harnessed for revolutionary technologies. Quantum cryptography uses entanglement to create unhackable communication channels. If an eavesdropper tries to intercept the message, the very act of observing the entangled particles disturbs them, breaking the entanglement and immediately alerting the sender and receiver. It's like having a secret messenger line, where any attempt to listen in instantly cuts the cord. Entanglement forces us to reconsider our place in the cosmos. If particles can be so intimately connected across galaxies, what does that say about our own separateness? We are all made of these same particles. Perhaps there is an invisible thread that connects us all, a fundamental unity that we are only just beginning to comprehend. The world is not what it seems. It's a place where particles can be in many states at once, and where they can be linked by an invisible, unbreakable bond. But the quantum world has another trick up its sleeve, one that allows particles to perform the ultimate disappearing act, to walk through solid walls. Chapter 4: The Ghost in the Wall. Imagine you are standing in front of a tall, solid brick wall. You want to get to the other side. You could try to climb over it, but it's too high. You could try to break it down, but it's too strong. In the world of classical physics, your options are exhausted. You are stuck. You simply do not have enough energy to overcome the barrier. Now, imagine you are a quantum particle. You approach the same wall. You, too, do not have enough energy to go over it. But instead of turning back, you do something impossible. You simply appear on the other side. You haven't broken the wall. You haven't climbed it. You have tunneled directly through it. This is not science fiction. This is a real and essential quantum phenomenon known as quantum tunneling. It stems directly from the probabilistic nature of the quantum world. Remember superposition? A particle doesn't have a single definite location. It exists as a wave of probability, a cloud of potential positions. This wave isn't strictly confined to one side of the barrier. A tiny, imperceptible part of that probability wave actually extends through the wall and emerges on the other side. This means there is a small, but non-zero, chance that if you look for the particle, you will find it on the other side of the barrier, even though it lacked the energy to classically cross it. It's like throwing a tennis ball at a wall 1,000 times. In our world, it will bounce back 1,000 times. In the quantum world, every so often, one of those throws will just go through. The probability of this happening for a large object like a person is so infinitesimally small that you would have to walk into a wall for longer than the age of the universe to have even a remote chance of tunneling through. But for the tiny particles of the subatomic realm, it happens all the time, and it is absolutely essential for our existence. The sun, the very source of our life and energy, shines because of quantum tunneling. The core of the sun is a powerhouse of nuclear fusion, where hydrogen nuclei are fused together to form helium, releasing enormous amounts of energy. However, according to classical physics, the sun's core isn't actually hot enough or dense enough for this to happen. The hydrogen nuclei, which are positively charged, repel each other so strongly that they shouldn't be able to get close enough to fuse. They are like cars trying to drive up a steep hill but running out of gas halfway. They just don't have enough energy to reach the top. But quantum tunneling saves the day. Even though the nuclei don't have enough energy to overcome the repulsive barrier, their probability waves leak through it. Every so often, two nuclei will tunnel through their mutual repulsion and find themselves close enough to fuse. It's this quantum cheat, this impossible leap through a solid barrier, that allows the sun to burn. Without quantum tunneling, the stars would not shine, and life on Earth would never have begun. This phenomenon is also at the heart of many modern technologies. The scanning tunneling microscope, which allows us to see individual atoms, works by measuring the tiny electrical current created by electrons, tunneling from the microscope's tip to the surface being studied. Flash memory, the technology that stores data in our phones and computers, relies on electrons tunneling through an insulating barrier to write and erase information. Quantum tunneling reveals a universe that is far more fluid and permeable than we imagine. The solid walls we perceive are not absolute. The barriers we face are not always insurmountable. The universe has a built-in loophole, a secret passage that allows for the impossible. It teaches us that reality is not governed by rigid, deterministic laws, but by probabilities and chances. There is always a possibility, however small, of finding a way through. This brings us to one of the deepest mysteries in all of science. We've seen that particles exist in a ghostly state of superposition, that they can be spookily connected, and that they can tunnel through walls. But all of this happens in the unobserved world. What happens when we look? What is the role of the observer in this quantum drama? The answer will challenge the very boundary between mind and matter. Chapter 5. The Power of a Glance. In every story, there is an audience. In every play, there is a spectator. But what if the audience could change the play just by watching it? What if the act of looking at the actors forced them to choose their lines, to pick a single path from an infinity of scripts? In the quantum world, this is precisely what happens. And you are the audience. This is the observer effect, and it represents the most profound and philosophically charged puzzle in quantum mechanics. As we've learned, before a particle is measured, it exists as a wave of possibilities, a superposition of all its potential states. This is described by a mathematical tool called the wave function. The wave function is the complete description of the quantum system. It's the spinning coin, the ghost in the machine, but the moment an observer, and this can be a human scientist, a simple camera, or any measuring device, interacts with the particle, something dramatic happens. The wave function collapses. The cloud of possibilities instantly evaporates, and the particle is forced to choose one definite state. The spinning coin lands. The electron appears at a single point. The alive and dead cat becomes one or the other. The universe, it seems, holds its breath until we look. A famous experiment that demonstrates this with stunning clarity is the double-slit experiment. Imagine firing tiny particles, like electrons, one by one at a screen with two narrow slits in it. Behind this screen is a detector wall that records where each electron lands. If you close one slit and fire the electrons, they behave as you'd expect. They pass through the open slit and form a single band on the detector wall, just like throwing paintballs through a doorway. If you do the same with the other slit, you get another band. Now, what happens if you open both slits? Common sense tells us we should just get two bands, the combination of the two previous results. But that's not what happens. Instead, a completely different pattern emerges on the detector wall, an interference pattern, a series of multiple bright and dark bands. This is the classic signature of a wave. It means that each single electron, traveling alone, somehow passed through both slits at the same time, behaving like a wave that interferes with itself. It was in a superposition of going through slit 1 and slit 2 simultaneously. Now comes the truly mind-bending part. The physicists, perplexed, decided to watch the electrons to see which slit they actually go through. They placed a tiny detector at each slit to record the electron's path. The moment they did this, the moment they observed the electron's choice, the interference pattern vanished. The electrons stopped behaving like waves. They started acting like simple particles again, forming just two bands on the final screen, as if they knew they were being watched. The very act of measuring which path the electron took forced it to choose a path. The glance of the observer collapsed its wave function from a state of both to a state of either-or. This raises a monumental question. What constitutes an observation? Does it require a conscious mind? Or is any physical interaction with another system enough to cause the collapse? This is the heart of the measurement problem, and physicists are still debating it today. Some interpretations, like the Copenhagen interpretation championed by Niels Bohr, suggest that the act of measurement itself is what fundamentally changes the system from the quantum to the classical world. Others, like the many worlds interpretation, propose something even more radical, that the wave function never truly collapses. Instead, every time a measurement is made, the entire universe splits into multiple branches. In one universe, the electron went through the left slit. In another parallel universe, it went through the right. In one universe, Schrödinger's cat is alive. In another, it is dead. In this view, all possibilities are realized in a constantly branching multiverse. Regardless of which interpretation you favor, the observer effect shatters the classical idea of a detached, objective reality. It suggests that the world, out there, is not separate from us in here. The act of knowing is an act of creation. By measuring the world, we participate in shaping it. We are not just passive witnesses to the cosmic drama, we are co-authors of the script. This isn't just a physical principle, it's a powerful metaphor for our own lives. The attention you give to something changes its nature. The focus you bring to a problem helps define its outcome. The questions you ask of the universe determine the answers you receive. We've seen the particle as a wave of possibility. But what is it, really? A wave or a particle? The truth is stranger than either option, a duality that lies at the very heart of matter. Chapter 6. The Two-Faced Universe. Imagine meeting someone who is, by turns, a meticulous, detail-oriented architect and a free-spirited, wildly creative painter. In their office, surrounded by blueprints and spreadsheets, they are all logic and structure. In their art studio, splattered with paint, they are all intuition and flow. They are not one or the other, they are both. Which personality you see simply depends on where you meet them. This is the closest we can get to understanding one of the central paradoxes of the quantum world, wave-particle duality. For centuries, the debate raged in physics. Is light a wave, like a ripple in a pond? Or is it a stream of particles, like tiny bullets? Isaac Newton championed the particle theory, while his contemporary Christian Huygens argued for the wave theory. For a long time, the evidence seemed to favor waves. Experiments showed that light could diffract, bend around corners, and create interference patterns, all classic wave behaviors. But then, at the dawn of the 20th century, things got complicated. Max Planck, studying black-body radiation, found that energy was emitted in discrete packets, or quanta. A few years later, Albert Einstein took this idea and ran with it. In his explanation of the photoelectric effect, where light shining on a metal can knock electrons loose, he proposed that light itself is made of these particle-like quanta, which we now call photons. Suddenly, the particle theory was back. So, which is it? The answer, as quantum mechanics revealed, is that it is both, and not just light. Everything, electrons, protons, atoms, even molecules, exhibits this strange two-faced nature. Every particle in the universe has both wave-like properties and particle-like properties. Which face it shows you depends entirely on how you look at it. It depends on the question you ask. The double-slit experiment is the perfect illustration of this duality. When you don't check which slit the electron goes through, you are asking a wave question. You are setting up an experiment to test for wave-like behavior, and the universe answers, I am a wave, by creating an interference pattern. But when you place a detector at the slits, you are asking a particle question. You are setting up an experiment to determine a specific location, and the universe obliges, answering, "I am a particle," collapsing its wave function and passing through one slit or the other. It cannot be both a wave and a particle at the same time. These two aspects are complementary. The physicist Niels Bohr called this the principle of complementarity. A quantum entity's wave and particle natures are like two sides of the same coin. You can see one side or the other, but you can never see both at once. The more you know about its particle nature, its position, the less you know about its wave nature, its momentum, and vice versa. This is the essence of Werner Heisenberg's famous uncertainty principle. It's not a statement about the limits of our measuring devices. It is a fundamental, built-in property of the universe. There is an inherent fuzziness to reality. You cannot simultaneously know with perfect precision both where a particle is and where it is going. The more you pin down one, the fuzzier the other becomes. Think of it like trying to take a picture of a speeding car. If you use a very fast shutter speed to get a crisp, clear image of the car's position, the picture will be so frozen in time that you have no idea how fast it was going. If you use a long exposure to capture the blur of its motion and determine its speed, you will have no idea of its precise location at any given moment. This duality shatters our classical, common-sense categories. We like to put things in neat boxes. Is it this, or is it that? The quantum world refuses to be boxed in. It is this and that. It is a realm of inherent ambiguity, where particles wear masks, and the mask they choose to show you depends on the experiment you design. It tells us that reality is not a static, definite thing. It is a dynamic, responsive process. The universe is in a constant dialogue with the act of measurement. So far, our journey has been one of observation, of learning the strange new rules of this hidden world. But knowledge, if it is to be truly transformative, must lead to action. How can we take these mind-bending concepts, superposition, entanglement, tunneling, and duality, and apply them to our own lives? It's time to move from theory to practice, to build not a physical machine, but a new kind of intuition for navigating our own reality. Chapter 7. The Quantum Toolkit for the Mind. We have journeyed deep into the strange and beautiful landscape of the quantum realm. We've encountered ghostly superpositions, spooky connections, and particles that walk through walls. It's easy to leave these ideas in the domain of physics labs and complex equations as curiosities with little bearing on our daily lives. But the principles that govern the universe, at its most fundamental level, are not just abstract rules for tiny particles. They are powerful metaphors and mental models that can reshape how we think, how we create, and how we approach the challenges and possibilities of our own existence. This is our practical chapter. We are not going to build a quantum computer, but we are going to build a quantum intuition. We will forge a toolkit for the mind, using the core concepts of quantum physics as our guide. First, let's take the principle of superposition. In the quantum world, a particle exists in a cloud of potential states until it is measured. Let's apply this to our own potential. Before you make a decision, before you commit to a path, you exist in a superposition of countless possible futures. You have the potential to be an artist, an entrepreneur, a scientist, a traveler. These aren't just daydreams. They are real, accessible possibilities within your personal wave function. The act of making a choice, of taking a concrete step, is the act of collapsing that wave function. You choose one reality from the cloud of potential. This mindset is incredibly freeing. It means you are not defined by your current state. You are defined by your potential. And it puts a profound responsibility on the choices you make, for it is your focus and your action that turn possibility into reality. So, our first mental tool is the superposition mindset. When faced with a decision, big or small, visualize yourself not as a fixed point, but as a wave of potential. Explore the different possibilities in your mind without judgment. Then, when you choose, do so with the awareness that you are actively creating your reality from an infinite field of options. Next, let's consider entanglement. Two particles linked forever, their fates intertwined no matter the distance. This is a beautiful metaphor for connection and influence. Think about the ideas, projects, and relationships in your life. We often treat them as separate, isolated things. But what if they are entangled? Our second tool is the entanglement mindset. Look for the invisible threads connecting the different areas of your life. You might find that a breakthrough in your personal wellness is spookily entangled with your professional creativity. Solving a problem in one domain might instantly clarify a challenge in another, seemingly unrelated area. This mindset encourages holistic thinking. It reminds us that we are not a collection of separate roles, but a single, interconnected system. Nurturing one part of your life will inevitably influence all the others. Finally, let's harness the power of quantum tunneling. A particle, facing an insurmountable barrier, simply appears on the other side. This is the ultimate model for nonlinear problem solving. When you face a wall, a creative block, a business challenge, a personal obstacle, our classical instinct is to try and go over it, work harder, or break through it, use brute force. But sometimes, there isn't enough energy for that. The tunneling mindset offers a third way. It's the search for the unexpected, paradigm-shifting solution. It's about stepping back from the barrier and asking, what if the rules aren't what I think they are? It's the sudden insight, the aha moment that doesn't come from a linear progression of thought, but seems to appear out of nowhere. To cultivate this, allow yourself to be playful, to ask what-if questions, to embrace uncertainty. The solution might not be on the logical path you're trying to force. It might be waiting on the other side of a conceptual wall that you only need to allow your mind to tunnel through. Using these tools, the superposition mindset, the entanglement mindset, and the tunneling mindset is not about pretending we are quantum particles. It's about learning from the fundamental nature of reality. It's about being more creative, more resilient, and more aware of the deep, interconnected, and probabilistic world we inhabit. These concepts show us that the universe is not a rigid, deterministic machine, but a dynamic, creative, and participatory process. We have explored the building blocks. Now it is time to step back and see the entire structure, to listen to the music that these strange rules compose. Chapter 8. The Unfinished Symphony. We began our journey with a simple grain of sand, and in it we discovered a universe. We found a world that operates on a logic so alien it seems to defy our own, yet so fundamental that it builds everything we know. We learned that at its core, reality is not solid, but a shimmering haze of possibility, a state of superposition where a particle can be in all places at once until the moment of observation. We witnessed the spooky, instantaneous connection of entanglement, an invisible thread that binds the fate of particles across the cosmos, suggesting a deep, non-local unity to the fabric of space and time. We saw the impossible made possible through quantum tunneling, the ghost-like ability to pass through solid barriers, a phenomenon that powers the very stars that light our sky. And we grappled with the profound mystery of the observer effect and wave-particle duality, discovering that the universe is not a static picture we passively view, but a dynamic dialogue. The questions we ask, the measurements we make, help to shape the answers we receive. It is a two-faced reality, showing us a particle or a wave depending on our experimental intent. These are not just separate, disconnected facts. They are the notes in a grand, cosmic composition. Superposition provides the harmony, the richness of all possible notes playing at once. Entanglement provides the resonance, the way one note can influence another across the entire orchestra. Tunneling provides the unexpected leaps in the melody, the surprising transitions that give the music its life. And the observer, the listener, by the very act of paying attention, coaxes the symphony from a cacophony of potential into a single, beautiful strain of reality. This is the great insight of the quantum revolution. The world is not a collection of things. It is a network of relationships. It is not a noun. It is a verb. It is a constant, shimmering, probabilistic dance. And we are not separate from this dance. We are made of the same quantum stuff, governed by the same strange and wonderful rules. Understanding this changes everything. It dissolves the hard line between us and the universe. It suggests that the potential that exists in a single particle also exists within us. It hints that the connections that bind distant stars might also bind us to each other and to the world in ways we are only beginning to fathom. The journey into the quantum realm is not just a scientific endeavor. It is a personal and philosophical quest. It teaches us humility, forcing us to admit that our common sense is a poor guide to the ultimate nature of things. It teaches us wonder, revealing a universe far more mysterious and magical than any myth or legend. And it teaches us about our own power, the power of focus, of choice, and of participation in the unfolding story of reality. Our understanding of this realm is still in its infancy. We are like children who have just heard the first few notes of a vast, unfinished symphony. There are still deep mysteries to solve, new melodies to uncover, but we have heard enough to know that we are part of something extraordinary. We are not just matter, we are possibility. We are not just separate beings, we are entangled. We are, each of us, a unique expression of this strange, beautiful, and fundamentally interconnected quantum cosmos. And the music is waiting for us to listen,